Okay, hello everyone. Happy Friday. Thanks for staying till today. I know it has been very stressful meeting so many people in a week. I haven't talked to so many people in a week than the past 2 years. And especially people not wearing pajama in front of my computer screen. I have some announcement. I'm not joking. 9:30, students, please gather at the stair. There's a group photo of all students. And if you look like a student and you can mix in, you can still join, like me. The second announcement is the lost and found. The registration desk, there's sweaters, and there's a ring there. So if you lost your wedding ring, please get it. Otherwise, there'll be trouble. What else? No more jokes. So the first item on the agenda is probably the peak moment of the whole CEDAR workshop, the poster prize announcement. Matt, you have the floor.
All right, good morning, everyone. I do not look young enough to mingle with the students unnoticed. So I was very happy to be asked to work with Ja and Lindsay and Indawaki on organizing the poster contest this year. For me, when I was a student, it was one of the highlights. It was also one of the most terrifying times of the conference, but it was also very exciting and a very meaningful thing. And I want to thank everyone who was involved in the poster competition, and I mean the students. We'll thank you again in a minute, and also the judges, and also Astrid as well, who kind of kept us moving in the right direction and on task. So next slide, please. Okay, so this is the participation information. On Tuesday, we had the Mesosphere Lower Thermosphere poster. It was 39 posters. And on Wednesday, we had the IT posters, and it was 34 posters. And again, I want to emphasize how important the poster session is to CEDAR. It's the biggest allotment of time on the schedule, and that's for a reason. It's because it's such a highlight of the conference and so important. And so I want to just stop now and thank everyone who prepared a poster, every student who poured, time and time again of their work into preparing a poster. Let's just thank them really quickly. It was a fantastic session. Next slide, please. Okay, the other people that I really need to thank. So if you haven't judged the poster contest before, I would highly recommend that you volunteer for it next year. It's a wonderful experience. It's also a very lengthy experience. It takes the better part of the day to go through, judge all the posters. We'll show you how I'll outline how we did the rankings in a minute. But I want to thank, I'm not going to read all 27-ish of these names, but I want to thank everyone who served as a judge for either the MLT or IT sessions. Huge commitment, and I watched everyone doing their rankings. Everyone was very diligent and worked very hard to give helpful and constructive comments to the students. So let's thank our judges, please. And also, again, Astrid. I sent Astrid about 400 emails the day before the competition. You know, I've judged this probably 4 or 5 times, and I've been to CEDAR for 15 years, and I still couldn't remember how it worked for some reason. So now probably I do, but thank you, Astrid. Next slide, please. All right, so I just wanted to say a word about the evaluations. So there were 2 rounds of judging. One of them occurred before the poster session, and it was intended to be without the student. We were judging the visual quality of the poster, how the information was laid out, how well stated the problem was, how representative the title was, and so on and so forth. And you will get, if you're a student that was in the poster competition, you will get your judging sheets back. They are actually at the registration desk, so during the break you can go get them for both round 1 and round 2. And they should have written, most of them will have written comments on them, just explaining either why the judge scored things the way they did, or maybe making suggestions for future improvement. And so these comments are really, please don't take this harshly. These are meant to try to help you improve your work and to try to make suggestions for things that might be useful for presenting it in the future. The judging process is not perfect, but we try very, very hard to do a good job and to make useful comments to everyone. Okay, so this is just the front side of the first round score sheet, and I talked about the written comments. There were 2 rounds of scoring, one without the student present, that happened before the session began, and one during the session where you had the judges visiting you and scoring based on oral presentation and scientific quality of results, and so on and so forth. So there were 2 numerical scores that were assigned, and then after that, there was actually considerable deliberation. We picked a top group, and then we revisited all of those posters again, and then we all looked at them as a group of judges and deliberated which ones we felt were best, followed by rank order voting. So I just want to say a little bit about the process. It is a process. It's not perfect, but we try to do it as good a job as we can. All right, so next slide, please. This is important. Please pick up your evaluations at the registration desk if you're a student. And again, it's supposed to be constructive, helpful feedback, and we hope that it's useful to you for future endeavors. Next slide. Okay, so I'll do the MLT awards first. These are from Tuesday. The head judges were Jia and Lindsay. Next slide, please. So, the undergraduate award goes to Ishida Solanki for Autonomous Platform for Distributed Ionospheric Studies and Citizen Science Initiatives. So if you're receiving an award, please come up to the stage. If you're receiving an award and you're here, please come up to the stage because we have an award certificate to give you. So Ishida Solanki, are you here? Okay, that's fine. It's pretty early. I don't blame anyone. Okay, so next slide, please. So that was our undergraduate winner from Tuesday. So honorable mention. We do give out a prize for the undergraduate poster. We give out first, second place, and honorable mention for the graduate students. I should have mentioned that. That's the format of the awards. All right, so honorable mention, Sean Dempsey for interannual variability of the 12-hour tide in the mesosphere and lower thermosphere and 15 years of meteor radio radar observations above Rothera. Excuse me, I'm sorry for butchering your title. Sean Dempsey, please come up if you're here.
Thank you so much. Oh, brilliant. Thank you.
We'll just stand up here and get a picture at the end of it. Yeah, so if you're getting an award, please stand on the stage, and I think Astrid or someone will take a picture of us at the end. All right, excellent. Next, please. So second place for the MLT is Claire Gask for volcanic disruption of the equatorial ionosphere, icon observations of the Tonga eruption. And do make sure I gave you the right award with the right name on it. Congratulations.
Thank you.
All right. Next, please. First place for is Zishan Kao for Southern Hemisphere Mid-Latitude MLT response to the 2019 Southern Hemisphere sudden stratospheric warming revealed by 2 meteor radar observations and SD Wacom X simulations. Cheers. Congratulations. All right, so now on to our Wednesday winners. Next slide, please. Oh, sorry, this is just a placeholder. Next slide. All right, so undergraduate award, Diego Sanchez from New Jersey Institute of Technology. And here's where I got everything out of order. Here we go. Investigation of traveling ionospheric disturbances detected with ham radio transmissions. Good job.
Thank you. Thank you so much.
All right, next slide, please. We had 2 excellent undergraduate posters in the Wednesday competition that we wanted to recognize and award. So the second one is Ronaldo Rojas, forecasting spread F at Hicamarca. Ronaldo, if you're here, please come up. Next slide, please. Okay, honorable mention, graduate student honorable mention for Wednesday, Binghui Wang, topside F region O+ and H+ drifts inferred from Arecibo ISR long pulse echoes. Nicely done. All right, next slide. Second place, Arunima Prakash for interannual and diurnal variability of PMCs using 10 years of LIDAR and 14 years of SIPS observations at McMurdo. Congratulations. All right, and lastly, first place, Yu Hong for interhemispheric asymmetry of the ion convection boundary expansion during the 8 to 10 October 2012 storm. Nicely done. All right, and so that concludes our awards. Next slide, please. I think that might. So I just want to leave this up here, and these are our winners again from Tuesday and Wednesday. I want to thank everyone who participated, especially the students. We saw so much really good, high-quality work. I'm very impressed, and I'm very encouraged about the future of our field, looking through these posters at what all of the students are doing. So one more time, thank our students. And yeah, okay. So yes, the head judges, please come up so we can get a picture with everyone.
Oh, okay. There's someone with a camera. That's good. It's not easy.
We good?
Are we? Oh, okay.
All right. That was quick.
I wasn't looking at all.
One more time for Lindsay. She wasn't looking. All right. Cheers, everyone.
Yeah, thanks, Matt. It was fantastic. And please also, the winners, please also check your date of birth if it's correct on your certificate. That's a joke. Okay, the next item is the Grand Challenge report by Katie Greer, coordinated ground and space-based observations of the ionosphere and thermosphere system. It's very important. You have the floor.
All right, so thank you for everyone who made it to Friday morning. I also want to thank everybody who participated in this grand challenge over the last couple of years. If we go to the next, we have a, okay. So the purpose of this grand challenge was to look at integrating different views to gain a comprehensive understanding of the system, which is kind of part of the charge of CEDAR, but we wanted to take advantage of the great instruments that we have on the ground and look at some of the new space-based assets. So we proposed this back in 2019, so it's been more than 3 years, but in the first year, we wanted to do the initial sharing of current observational capabilities. We really wanted to have an understanding of what we could do and the potential for opportunities. So we did a survey of the current ground-based instruments, the space-based assets. So this was when ICON and GOLD were coming online. We also had COSMIC 2, and then also some models and data assimilations that can put maybe some instrument observations into context or really elucidate some aspects of the system. And then we also tried to do some planning for future campaigns. The second year was a COVID year. This was 2020. So I believe we had a virtual meeting. And again, I want to thank everybody who made the effort to participate during those challenging times. And And in that meeting, we started to share some of the initial results of some of these coordinated observations. So we did inner comparisons of instruments, and then also some model data comparisons. We shared the new scientific results that we'd been finding, and planning and coordinating more campaigns. So one of the strange things with COVID happening is we kind of had a do-over of year 2. I call it year 2 point COVID. And we kind of continued the charge from the previous year. So again, we were doing similar things, but we were also starting to discuss lessons that we had learned from some of these campaigns that we could apply in the future. So this year, we had more campaign findings that were exciting to discuss, but we also had some really great information on lessons learned and what we can do in the future to get the most bang for our buck. What are we, how can we leverage these technologies the best to our ability? We had a really great workshop this year. I want to share a little bit about what we talked about. So Richard Eastes, the PI of gold, brought some really great gold comparisons with other instruments and what can be done. Rob described some sounding rockets that they had done with an experiment that looked at integrated currents. In that, Phil Erickson gave a really great presentation on the careful preparation and coordination of data conjunctions with ICON. Jim Clemens also had some great information on the 2 Dynamo rocket launches that they were looking at winds and comparing with both ICON, I believe, and like MSIS. Jens brought some really great work looking at using Cosmic 2 and tides. Chen Wu gave us an update on Cosmic 2. So that data is available, and if you want to use it in your studies, you should go find it. Aaron Ridley gave a really fascinating talk on using tidy data. I know the timed mission is about 20 years old, but they are still producing great data, and Aaron really showed that in certain circumstances, you can really use that data. And for those students who don't know, tidy is a wind instrument, basically, on timed. Kamal looked at sun stratospheric warmings with Doppler imager, scanning Doppler imager, and Sarav also brought some great results comparing gold during a solar eclipse and what we can learn from that. So I just went through that, but just again, you know, there's some really great rocket events, campaigns that happened that the community should take notice of. And then again, we have this, we're in this great era where we have ICON, gold, and cosmic all at the same time, and we really are living in a great era where we get to do science with those. For me, one of the really important aspects of this final year was thinking about lessons learned, and I just want to communicate to the community what we came up with so that you can hopefully apply them to future campaigns or even studies. One of the things that was brought up is that calibration and validation are very important, especially for new instruments and missions, but it's not really sexy, and you can't really, it's going to be really hard to get students excited about coming to your institution to do that, but we still need to do it. So to do it, we need investment, support, and planning for the instruments and the scientists. So the instruments that you might want to do CalVal with, they need maintenance. They need investments so that they're available when your instrument or mission comes online, and then the scientists you need operating, and you need to support the scientists who are going to help you do the analysis of that instrument data's product. And I'm also saying this in communication to, hopefully, the agencies. We need help with that. If you have a special operation that's needed with an instrument, that's going to require more planning and lead time. And that's everything from the ground-based community to also the space-based community. So I can think, I'm familiar with gold. If you have gold can't just turn around and implement a new special operation in 30 minutes. It takes a lead time of 10 to 12 days. And so you really need to think about what kind of events that you can look at in that context. The conjunction tools are fantastic tools. They're helpful. Well, they're greatly appreciated. So one of the tools that we saw a lot of was the ICON tools to look at conjunctions. And then there was a plea for more communication and discussions with instrument operators. So do it early and do it frequently. Here at CEDAR is a great opportunity. If you're a student, approach those instrument operators and find out what they are interested in helping with and how you can get involved. And then a lot can be done by email, as we've discovered throughout the pandemic. Science got done. Let's take advantage of some of these technologies and make sure that discussion and communication continues to happen. And then the last thing that comes up repeatedly is we need to have some interagency cooperation and coordination to get these campaigns done. And in general, the ground-based community might be with one agency and space-based might be with a different agency, and we need to find a way to coordinate and work together. And that's pretty much all I have. One other thing I really want to mention, we had some really great student help at our workshop. And not only do I appreciate the students who participated in our workshop, but Marie Bowles did a fantastic job really helping make sure this meeting came together, especially since not all the co-conveners could be here today, or this week. So thank you.
Yeah, thanks, Katie. I'm very impressed by you listed the lessons you learned from this grand challenge. I think it will be very useful for the future GDC coordination with the ground-based measurements. Okay, the last but not least science highlight. That's by Corwin Wright from University of Bath. Waves, talk about the waves from the Hunga Tonga eruption. And Corwin is a very passionate and entertaining speaker.
That's getting the hopes up, isn't it? Okay, hello everyone, and thank you for all coming on the day after Banquet Day. I'm impressed that so many of you are here, to be honest. As Jar said, I'm going to talk today about atmospheric waves triggered by the 2022 Hunga Tonga eruption. We've all heard a lot of talks about that this week. Hopefully the perspective of this one will be a little bit different because I'm primarily a stratospheric scientist. It'll be a perspective slightly down in the atmosphere, which might have some novelty. Okay, so I'd like to start with a diagram of the volcano before its eruption and a diagram of the volcano after its eruption. And this is a mural that I saw in Zagreb on holiday last week, but it's actually quite accurate, it turns out. So the volcano's here, massive steam plume coming out, and then waves coming off it. So I quite liked it. I thought it would be very useful. Looking more scientifically, though, here's some imagery that I've taken from the BBC's website that shows the island before the volcanic eruption. So what we have here, this is about a week before the big eruption, and you can see there's two islands here, Hunga Ha'apai, Hunga Tonga, and then this sort of joining island volcanic crater in the middle. And that was sat there quite a while, steaming away as volcanoes do. A few days, though, before the big eruption, this happened. So this is a mid-sized eruption that happened, I think, 2 or 3 days before. I'd need to check the numbers. And that did this. So that's now Hunga Ha'apai, that's Hunga Tonga, big gap in the middle where there was an island. And that shallow water made things very interesting. So the shallow water is the exciting bit of what's going on here. So let's rotate that map down and look at it like this. And let's look at the context. And I've got the really high-quality graphics that I've broken out for you of there's the Earth and there's the magma vent below. And the magma vent is sort of below the watery bit rather than below either of the bits of island. And on the time the eruption went off, the magma went up. I'm not the best at slide design, but you get the idea. Okay, and because it went up into the shallow water, that blasted steam into the air, and it blasted a lot of steam into the air. It's unusual, I said in response to a question the other day, because this water is shallow, but not really, really shallow. So it's deep enough that it blasted a lot of water into the air, but it's not so deep that it squished the eruption down to where it didn't matter. And because of that, this massive plume of steam got to above 50 kilometers, which is excessive. In this region, I think it might have been in the mesosphere. We know that's the case because we've got measurements from EASI. And these are measurements from EASI, which is a hyperspectral sounder that ESA run. And this spot here is water relative to climatology in this region. And if you look really closely, you'll see there's a white square there. And even though the EASI team know the eruption is there, they could not get the retrieval to converge on the amount of water vapor that was coming off. So it's really, really large amounts of water. So my next question is, how much energy did this water transfer to the atmosphere? And what we did is we tried to... Sorry, I keep rotating my head and getting louder. I can hear it myself. I'll try and look that way. What we did is we looked at the pressure anomaly coming off that volcanic eruption, off the waves from that eruption, to try and work out how much energy there was in the eruption. So this is distance from the source. This is the pressure anomaly that we saw, and these are just different data sets that we had. And you see lots of different points, reasonable error bars, and we can get a nice fit to that. And if we look at the numbers in that and look at some methods of computing this, we can work out the size of the eruption. And we did this 3 different ways. The first one was basing it on a nuclear explosion. There's a paper from 1970 that gives this equation. That gave us 20 exajoules, which is a lot of joules. A different method based on previous volcanoes, that gives about 10 exajoules. And then if you do a really simple physical argument, just assume uniform pressure below the umbrella, you get about 18 exajoules. These are big numbers. And to contextualize it, we then looked at previous eruptions. So this is, again, distance, and these are all the different measurements. This is the energy on a log scale, and these are some previous eruptions. And we argue that, in terms of the energy transfer to the atmosphere, at least, if not the eruption itself, it was bigger than Pinatubo, definitely, and potentially of the same order of magnitude of error bars as Krakatoa in 1883, which is the really big boy of big volcanoes. So that's what happened there. And as a result, because there was this massive lump of water latent heat dumped into the atmosphere, it produced lots and lots of waves that came off. And I hope you appreciate the high-quality graphics of there being multiple waves coming off of different kinds. So we had 3 different kinds. I've got 2 on here, and I'll talk about the 3rd kind later. One of them was something we call a Lamb wave, and that's a surface-bounded external mode that's strongest at the surface and then decays exponentially with height. And then we also had a lot of gravity waves, primarily in the stratosphere because it's stratified, hence the name. And I'm going to talk first about the Lamb wave, and that'll be the longest section of the talk. So when I get to the end of that, you know you're nearly there. Okay, so this is a video of the eruption, and I'm afraid I don't remember what satellite it's from. I've had the animation on my desktop for a while. But this is the eruption. The reason the dark's coming across is because it's nightfall, so that's the Terminator just shooting across. And if you squint sort of early on, you might see sort of a light flash going outwards there. That's the effect of the Lamb wave on the atmospheric density in the troposphere. So it's big enough and powerful enough that it's squeezing the air in the troposphere to where you can see it from space, which is impressive, I think. And if we look at that as individual snapshots, what I've got here is brightness temperature perturbations due to the wave, and we've got snapshots every 20 minutes. The satellite measures every 10 or so, but it was too many panels. And you can see, oh, sorry, wrong button. How do I go back? There. Okay. So this is probably at the time of the eruption. I should say there was smoke coming off the volcano from about 4 a.m. The US Geological Survey thought the eruption was at 4:10. So that was what happened below the surface. But the stratospheric waves, as you'll see in a second, we backtrack to about 4:28. So this is the perturbations in brightness temperature at the beginning. And then as the eruption came out, you see this. and this is shooting out further and further out from the volcano in this radial form. And then in this last one, you can see some gravity waves coming out as well later on. This is a large area. This is a 20-degree box. It's not a small diagram. These waves are going a long way, and they're going very, very fast. Here's an animation that most of you have seen before. So this is by Matt Barlow, one of our co-authors, and this is over a period of about maybe 3 or 4 hours. So the eruption is coming out from here. You see this big land wave going across. If you squint, you can see some smaller waves in there. I don't think they're gravity waves because this is the troposphere. I think they're probably subsequent land waves and subsequent eruptions, because there were 4 subsequent eruptions. 3, sorry, there were 4 total. And then down here, you can see small stuff coming out for a while afterwards. Again, if you look at that as freezed frames, you can see these are about every 50 minutes. You can see here, 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 blah, 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 blah. The whole thing is going out over the whole Earth, really, really long distances, and it's still retaining a brightness temperature amplitude of about a Kelvin, which is fractionally quite large given how large an area it's diffused over. Here's another animation that we actually put together yesterday. I'm sorry it's a little bit scratchy because it's still quite new, but this shows the Earth's disk on the Tonga side. Tonga's here. This shows the Earth's disk at the antipode here. So this is the antipode in Algeria, and you can see the wave coming out from here, converging into there, going back again, and coming back here. So it's going around the Earth over and over again, and I think some places as many as 6 or 7 times. In the satellites, you can only see it a couple of times, but it's quite impressive. Yes, I think would be the answer. I think if you look at Himawari over the Pacific Ocean, you'll again see the wave in the appropriate place, but these 2 views show the interesting bits. So finally, we can look at the antipode, and this is the antipode here over Algeria. We can see, interestingly, whereas coming out from Tonga, it's a very, very circular, clean wavefront. By the time it gets to the antipode, it's actually sort of split up into lots of little bits. It's still converging quite effectively, but it's arguably 4 distinct waves, sort of like one here, one here, one here, and one here. And that's because of atmospheric effects and also surface friction effects, because it's the troposphere. And if you go back to the previous animation, you can see it there now. Now, if you're looking for it, you can see it coming in as lots of bits, and over there even worse. So out circular, but by the time it gets here, distinct wavefronts. And obviously, as it went around the Earth, those wavefronts got more and more messed up. And finally, we can look at the speed of that pulse and work out the eruption time from it. So again, we're using our surface pressure stations. These are in the yellow dots. And if this is distance from the source, and this is time in hours, and again, it's just the same data sets, we can very, very precisely pin down the average speed of that wave as 318 plus or minus 6 meters a second. That's almost exactly in line with what we predict from theory, because we worked it out from theory, and it's almost exactly in line with what we've seen from Krakatoa with 1880s observations. And this is how we know the explosion time was about 428 in the atmosphere rather than 410 at the surface. But both are true. 410 below the surface, but the water got up there by about 4:30. And then I think this is my last land wave slide, but who knows, there might be another one. This one just shows the effects of surface roughness on the wave. So this is 8:15 a.m. Sorry, this is 12 noon. This is 17:20. You can see here the wave is more or less along the grey line, which is what we expect theoretically, whereas here it started to split up off the perfect wavefront. And we think that's due to the surface roughness of North and South America, which is very, very bumpy. Ecuador actually has the highest point in the Earth relative to the center of the Earth. The Himalayas are actually a bit smaller. So that's what's going on here. It's pulling it off from the sphericity of the Earth due to surface roughness and to some degree weather, but more with surface roughness, we think. Okay, so that's my first conclusion. The leading land wave propagated around the Earth multiple times at a very well-defined speed that is well constrained by theory, and it was affected by weather and surface. Oh dear. I think the last word is topography. I don't quite remember myself, but I think topography is the word that's gone off the bottom of the slide. Okay, let's now move on to the gravity waves, and I'm talking here about the initial burst of gravity waves. So you have the eruption, and then the eruption generates the land wave and the gravity waves simultaneously, and then there's a convective flume cloud afterwards that generates more gravity waves. These are the ones from that initial explosion. So this is a figure that Neil Hindley produced for our paper, and it's very dense, very involved, but it has a lot of information in it. So what we've done is we've merged lots of different data sets, and then we composited them all onto an equal area map centered on Tonga. So each of these colors outlines a different instrument, and they're all at different heights, which are labeled on here. I should say these 3 instruments all measure the same 3 heights. We've just split them out to make it clearer that they're looking at different layers. And you can see close into the eruption at 9 a.m., there's these very, very sharp, dramatic fronts. And they're there in all layers of the atmosphere, and they're moving outwards. So 4 hours later, they're here. 3 hours later, they're here. They're moving it very effectively out over it. We see them in the Ionosphere as well, but I won't dwell on that. We see them in airglow at Hawaii. We got very, very lucky there, actually. The eruption was on the night of the full moon, so almost all the airglow cameras in the world didn't see the damn thing. But there is a camera at the Gemini Observatory in Hawaii that was just looking to see if there was cloud that happened to see it. And we got very lucky, and we got some very nice numbers from that camera. What I'm going to do is I'm going to focus on this here. So this is a pass of the air satellite going southwards, and it's taking about half an hour to do that. So you see little time labels, so 11 a.m., 11:10, 11:20, all UTC. And what we did is we looked at this slice, because it was the nearest one in time to the eruption, and we did some spectral analysis on it using the S-transform method. So the top slice here, this is the along track distance of the satellite, and this is the across track distance of the swath. And you see here, this is close into the eruption, this is further out. And in particular, this very fine feature here, that's the leading land wave, and then these are the leading gravity waves, and then this is other stuff going on later. And from these data, we can work out the amplitude of the waves, which I won't really talk about, and we can work out the wavelength of the waves, and that is a lot more interesting. And this is the 2D wavelength, so it's not a projection, it's actually the true horizontal wavelength. Now, the interesting thing about this is that we can look at it compared to theory. So I won't go into why, you can see it in the paper, but we can work out the vertical wavelength of this wave is over 100 kilometers, which is effectively infinite. Our calculations don't really change if you make it 110. And what you can do is you can work out from the dispersion relations and so forth the maximum permitted phase speed of a wave of a given horizontal wavelength. So the land wave, fixed speed by definition, but the gravity waves, the long horizontal ones can go at about 300, the short ones can go at much, much slower speeds. So this is what we were predicting theoretically, and the results we get absolutely beautifully correspond to this. So this is the same slice, just upside down, just so I can show the land wave in line roughly with the land wave. And this is that horizontal information. And I'm sorry if the colors are a bit washed out. But the land wave, that's here, that horizontal feature. That's going at the beginning, at the front, because it's going faster than everything else. The gravity waves, though, this is the long horizontal wavelength gravity waves. And as the wavelengths get shorter, they get further and further back, which means they're going slower. So we have this absolutely beautiful confirmation of this theoretical prediction of this maximum speed of a gravity wave. So these waves are going pretty much as fast as they possibly can, and they're dispersing from each other purely due to their physical structure. So it's an absolutely beautiful test of our gravity wave linear theories. This slide's a bit hard to interpret, but it's just showing that these waves also went around the Earth. So this is 3 time snapshots. I forget exactly when, 2 in the morning. Here, this wave is going this way, then it's going this way, and then it's going this way. So we can see the wave cleanly cross the antipode as well. So it's not just the land wave that went around the Earth repeatedly. The gravity waves also got at least as far as the opposite point. Beyond that, it gets a bit messy. There's a lot of background noise, and we can't really track it much further than the antipode, but it definitely made it around once. So there we go. So my second conclusion is that the leading gravity wave packets traveled at the maximum possible speed of a gravity wave. They couldn't have gone any faster in a stable atmosphere. And they split out into different speeds, purely defined by their physical structure. So it's a lovely test of our theories. Finally, I'm going to talk about the trailing gravity waves. So these are the little ones coming out of the convective plume. So for about 12 hours after the eruption, there was a big convective lump of grumpy angriness over the volcano, and that generated lots of waves that traveled outwards, much smaller than the big ones you saw before. These figures aren't terribly clean, but I genuinely spent about a day trying to clean them up, and this is the best I could do. What you're seeing is tropospheric brightness temperatures from the GOES instrument at 4 different times during the day. This is 4 hours after the eruption. This is 11 hours after that, so 15 hours after the eruption. And if you squint at these for a very, very long time, you can see phase fronts in the convective cap here. You can also see them here and a bit more sort of grumpily there. Here, they're incredibly faint, but starting to die away. And by this time, there's not really any convective phase fronts anymore. It's a bit hard to see. I realize I spent a very long time staring at this picture to see these things. So what we're saying is that the convective wave generation in this ash and water plume carried on for about 12 hours. And that made a lot of waves. So these are maps of the entire Pacific Basin from all the mid-stratospheric instruments we could put together. This is about 4 hours after the eruption. This is about 8 hours. This is about 12 hours after the eruption. And if you look at them, here, the phase fronts are sort of in this circle here. Here, they're going all the way out over the coast of the whole Pacific. And here, they're still going over the whole Pacific. This is an immense area, and there's just waves constantly coming across. These ones are probably the initial waves, but these ones are all the little baby waves going afterwards. They're covering an area of radius, probably 9,000 kilometers. It's absolutely immense. And to make a point of how immense that is, it is really big. This is a map from Hindley 2015 looking at gravity waves refracting downstream from the Andes. That looks like it's covering a large area, but that's about a tenth of the area of the Pacific Basin because the area around the pole is quite small. And that is probably the biggest consistent long-term source of gravity waves that we know of in terms of spatial area extent. I've also done work on looking at the waves coming off hurricanes. Gravity waves from hurricanes tend to fall down to background levels within at most 3,000 kilometers. So this is a factor of 3 by radius, so it's an immense factor by area covered by these waves. So my point there is that the little baby waves, the ones that are not the interesting ones, are still possibly the single biggest gravity wave source in terms of spatial extent ever observed, which is a little bit crazy, to be honest, because these are the ones we didn't really think about at first. We came and looked at them and sort of when we were about to submit the paper and realized just how excessive they were. Okay, I'd like to end with this slide and then a summary slide. This is a figure my colleague Neil Hindley's put together, and what it shows is all the different kinds of waves that we've measured coming off Hunga Tonga in the atmosphere. So this is the phase speed of the waves going along this axis, volcanoes there, and these are the different levels of the atmosphere. So this is the land wave that we saw at the beginning, and that's in several layers of that's exponentially decaying in amplitude, but it's going as far up as we can reasonably measure. And we certainly can see it in the mesosphere and lower thermosphere. Ionosphere, I think we see it in tech as well, but much more faintly. We then have the leading gravity waves. They're going a bit slower, and we're seeing them in the air glow as well. Then we have the baby waves later that are carrying on for a long time, again in all layers. And then I've not talked about them, but there's also a whole menagerie of different TIDs coming across. We mentioned them briefly on our paper, but David Timmons does a much better job in his paper, so I'd look at that as well, of course. You should look at ours first. And there we go. So finally, I'd like to draw some brief conclusions. So we argue that the Hunga Tonga eruption was unusually large and possibly, certainly in terms of energy transferred to the atmosphere, was the largest since Krakatoa in 1883. And definitely the largest in the period we've been able to observe gravity waves in the atmosphere, which is only about 20 years, routinely. The initial land wave went on the Earth at 380 meters a second, and it hit the antipode after about 18 hours, which is exactly consistent with the time we expect it to take, but dividing up a little bit. The gravity waves also went all the way around the Earth, a bit slower and splitting out by wavelength in a theoretically predictable way. And then finally, there were lots of smaller gravity waves, and they're still some of the largest aerial extent gravity waves we've ever seen. I should say the amplitudes are relatively small. They're very clear in the data, but they're not, in terms of momentum transfer to the atmosphere, they may not be the biggest, but I'm talking aerial extent here and distance traveled. So why do we care about this? Obviously, it's interesting in itself, and that's why we wrote the paper, to be honest, but we had to write some justification for the editor of why it mattered. And we argue it's a very good natural experiment for testing lots of things about wave propagation in the atmosphere. Firstly, you can use it to infer the basic atmospheric state, because you can see how the waves refract and how they split up, and that's a good measurement of how accurate your model's temperature and wind fields are. You can also use it to look at convective wave generation, because it's such a violent, aggressive source, it's very easy to characterize. And finally, this is something that I care about probably more than I should. It's a very useful way to separate the source term from the propagation term when looking at gravity waves. Because if you look at satellite gravity wave measurements, the big problem we always have is you see a wave, okay, where did it come from? How did it get there? They're the same problem. You can't untangle them. Whereas this one, we know where they came from. So if we see them somewhere, we know where they came from, we know how and can work out how they got there. And that's where I'd like to end. So this paper's been accepted at the journal Nature. It should be out in hopefully the next couple of weeks, but I thought that a month ago, so it'll be out when it's out. And there's a preprint available on ESAW in the meantime, which is essentially the same. I think the whole process we changed to maybe 3 sentences. So there we go. Thank you very much.
Great, thanks. On your slide where you had the land waves converging on the, or showing...
Sorry, I'm trying my best. There we go.
Where they were deviating from the uniform wavefront.
Yeah.
I just wondered how how it happens that the roughness over like the continents, North and South America, slow down the wave propagation.
Honestly, I'm not entirely sure. That's my colleague Matt might know, and I can, if you let me know, I can get you his email address so you can ask the questions. I'm very much the stratosphere guy and the lead author, but I think he has some solid theories for why. I just don't really understand them. I'm not smart enough.
Thanks.
Other questions? Ruth? I give you that.
Thanks, Corwin. Great talk. So with regard to this source versus propagation, are there any lessons for those kinds of studies you mentioned where we see things in we see evidence of gravity waves in satellite data? Does this study kind of provide any guidelines for that interpretation?
I think it's useful, particularly in pinning down our methods, because our methods are, to be honest, not terribly good. And if we know the propagation speed, which we do because we know it's getting the maximum speed, then we can, for example, test how good our wavelength measurements are in both horizontal and vertical. So it's very, very good at pinning down the accuracy there. And similarly, the modelers can do some of the things. If they're not getting propagation as you would expect, given they're at the speed limit, then there's probably a fault. So it's useful for particularly fine-tuning things that don't work very well, I think.
Okay, thank you.
Questions? How about Slido? Oh, Greer.
Fantastic work. I just wonder which wave, long wave or gravity wave, can more efficiently cause the TEC perturbation?
I would expect probably the gravity waves, because they're probably carrying more momentum. The land wave it's lasting a long time, but it's not transporting much energy. It's just one little pulse, whereas the gravity waves are continuous and sustained for a very long period. So I'm not an ionospheric scientist, but that would sort of, certainly in terms of momentum transfer through the stratosphere, that's what I would expect.
Yeah, thank you. Yeah, great talk. All right. I'm wondering the later you call the smaller gravity waves. So the initial one has 100 kilometer longer vertical wavelengths. What about the later ones?
There's been a paper by Manfred Erner on that that's been published since we submitted ours. I think he was getting in the order of the low tens of kilometers for the smaller ones. He measured it with Sabre. So it's a paper by Ern in GRL. I would look for the numbers for that.
Ah, yeah. Great. Okay, thank you.
Do we have any questions from Slido? Okay. No? Okay. Let's thank Corwin for this very...
Thank you all very much for your time.
Right. The next is the Grand Challenge final report by Aaron Ridley from Michigan, multi-scale IT system and dynamics.
Okay. I realized as I was watching the earlier report how different I put these things together. This is sort of like a final report for NASA in which I just go through and grab like all the abstracts of the papers and stuff that you submit, and you just dump everything and just like, here's the information. No lessons learned or anything. I'm sorry. Okay. And I should definitely say that Toshi should be the one who is giving this, because he has done a lot of work in this. So all of the credit should really go to him. So back in the day, before we submitted this as a Grand Challenge report, there were not very many papers actually being published on multi-scale ionosphere-thermosphere processes. But then UA got a Muri grant and started publishing stuff, and then we got our GC, and then the publications have really gone through the roof. And that's not necessarily because we did anything. It's just that the community seemed to be very, very interested in this topic during this time. Okay, so let's go through a bunch of the stuff that's been done. So Toshi, with a group of people, have published this review paper on the importance of the multi-scale processes, and really with a lot of the key people in the field who are studying this stuff. They published a paper last year on this. Okay. One of the things that has been done is the Themis All-Sky Imagers. You used to just be able to get these maps, which were fantastic, and you could play them as movies and everything. But Toshi has really taken the maps and tried to turn them into products which we can use in our models, where we can get total energy flux and average energy from the data. And so we can actually look at the effects of the aurora, small-scale processes on the thermosphere. And so this has really helped us model the small-scale effects much better. And so this continues that, and there's been a lot of work on the data assimilation of precipitation, trying to get like SUSY data into the models because the background models are so smooth and poor that you really need some sort of an assimilative technique to give you the structure and the intensity of the aurora. And so that has been moving forward also. And then there's been a lot of work on the multi-scale convection and aurora by Larry and Bill. And so basically looking at how streamers move and how those interact and how they lead to things like substorms and stuff like that going on in both the aurora and in the convection maps. And then, oh, that is big. Bill has basically taken new radar data, new SuperDARN data, and tried to embed, or not tried, has actually embedded regions of small scale data into the global scale fits. And so we can actually get, on a large scale, you can get the entire potential, but then in the small scale region, you can get the actual, like, really highly structured flows. So this is, once again, another really big thing for modelers like me, because we would like to be able to investigate the effects of these structures on the thermosphere. Okay, so then this is, there are a bunch of groups that are actually looking at this embedding small scale effects into global scale things. And so DOA and Jing have been taking measurements from incoherent scatter radars and embedding those into the large-scale patterns of Weimer, and then running Ionosphere-Thermosphere model and trying to see what those effects are. And so they basically have come up with this technique of integrating the electric fields in different directions so then they can actually just put that data pretty much directly into the model. And then they've also been working on doing the same type of thing with the aurora, taking data from Pfizer and embedding that into a larger pattern and then running the model with that too. And so this is an extension of the other work with the electric field. Okay, and then Shasha and her group have been working on basically looking at the effects of these things. And so she has been focusing with a number of people on polar cap patches. And so looking at the formation, evolution, and impact of those using models and TEC data and the electrodynamic patterns. And so looking at the evolution of them, of how they actually form and then move across the pole and then break up into blobs and stuff like that. And then the impact is looking at, I think that this is looking at things like scintillation effects and stuff. And then Urcha and other people have been looking at these super equatorial plasma bubbles. So basically you get these plasma bubbles that form and then evolve, and then they move to very high latitudes, higher latitudes than we really thought before. And so this is a new thing, which has been shown. They basically are tracking these equatorial bubbles, which people talk about as being obviously near the equator, but they're moving to very high latitudes. Okay. And then, this is basically, Shasha and her group have been basically taking TEC maps and doing some assimilation on the background maps and then coming up with other maps that actually show much more structure. So basically trying to take the nice, smooth TEC maps and then adding the structure back into the maps from the original data. Okay, and then this is from UA and her group. So basically looking at high resolution convection and precipitation maps to drive GITM, once again, what we were just talking about a little bit ago. So basically taking high resolution electric field data, high resolution particle precipitation data, and then driving a high resolution model, and then looking at the effects of those drivers, those high resolution drivers. And in theory, you'd like to do this over the whole globe, but in practice, we have data in limited regions. And so they show that that is very effective. Using these techniques of using the high resolution drivers is very effective. Okay, and then UA and her group have embedded a high resolution region inside GITM, which has allowed them to model both the large scales and the small scales at the same time. And they've used this to investigate things like the ionospheric reaction to typhoons. And so looking at how a typhoon sends up waves, as we just heard about, and then those cause ripples at the lower boundary of the model, and then you can use those ripples at the lower boundary of the model to investigate how that affects the TEC. And she's done this, her group has done this on these small scale regions, and can show these really detailed total electron content maps. And then this has also been done in a different version of GITM, where we can actually simulate just a very small region of the globe. And so looking at how earthquakes affect the total electron content. And the JPL group has been working on this. And they were looking at both earthquakes, and they show some of the comparisons, and you really have to squint hard, but they're great. And then this is from Erdal and his group, and basically looking at how gravity waves deposit energy into the thermosphere, and how that energy causes temperature changes and momentum changes, and how this is actually, like, I shouldn't use the word actually, this is a really important process that global models should take into account. And so he's been doing a lot of work on that. It's really interesting because they're actually putting this, I used the word actually again, they're putting this into models of Mars and other planets. So they're doing a lot of work on gravity waves and how the gravity waves affect the atmospheres of Earth and other planets. It's really fascinating. Okay, and then Sharon's group has been looking at gravity wave deposition also, and using a ray tracing technique to deposit energy from the lower atmosphere up into the thermosphere. Okay, and then Mears's group showed that Farley-Buneman instabilities are really important by basically doing a lot of simulations with like pick codes and stuff. And Mears is, I think, wins the award of covering the largest amount of scales in this, because he was looking at, I don't know, 1 inch by 1 inch or something like that. It's particle and cell codes. They're really just massive simulations where he can study the physics at an extraordinarily high resolution. And so he's basically shown that these Farley-Buneman instabilities cause larger conductivities in the atmosphere or in the ionosphere. And if you ignore these, then you're not really getting the conductivity correct. And so in large-scale models, when the velocities in the ions become large enough, or the electrons become large enough, you're missing a lot of the physics, and so you need to account for that. And so he worked with the Boston group and put this physics into the TIE-GCM and into the LFM, and has shown that when you include this, you get pretty different results. Even on the, so you take basically the microphysics, you implement it in a very large-scale model, and you get very significant differences. And so this is something that other models should probably take into account too. Okay, and then Toshi and company published this book in December of 2021, which is cross-scale coupling and energy transfer in the magnetosphere, ionosphere-thermosphere system. And that basically is summarizing a lot of this work that has been going on. And then there's going to be there has been AGU sessions from 2018 through last year, and they've gotten a fair number of submissions, and then there will be another fall meeting session this fall. And so if you are interested in submitting to that, definitely see Toshi and company. And that is it. We feel like this has been an extremely successful grand challenge. So thank you very much for participating in it.
Thanks, Aaron, for the very nice summary. Any questions for Aaron? Okay.
This is exactly what you want for like a final report. No questions.
No question asked. Okay,
Done.
Perfect. All right. Okay. All right,
Okay,
thanks.
Thank you.
Yeah. Okay, the final remark would be Larisa.
Okay, before I start with final remarks, I have to make an announcement. It seems like we have a problem with student post-evaluations for Wednesday. Evaluation forms disappeared. They were available outside, stack of forms, and they are nowhere to be found. So judges put enormous amount of work into forming those evaluations. We will be looking at some ways to convey some of the information to students from whatever records are available, but at this point, we do not have them. I don't know if there are any updates. We just found a few minutes ago, so there are no updates on this. Okay. Okay, I'm really sorry. This is really unfortunate circumstance. I don't know. I really don't know what happened. If somebody took by mistake, or so where they all could go. So I will. I have some final notes, final remarks to share with you for today. First remark, these are really quick thoughts put together at 3 a.m. If student evaluation of poster judges would judge me for this presentation, I would not score well. So a lesson from this to all students: please do not put together your presentation at 3 a.m. Okay. Overall, we heard a lot of good comments about this meeting. We're really happy to be together, to see scientists, students coming together, communicating, discussing. Overall, I think CEDAR-22 is a great success. We had a really good number of participants. We had 275 people in person plus 52 virtual. Overall number of people is slightly below our usual CEDAR participation for pre-COVID years, and by far exceeds what we expected for this meeting in person. We actually really had concerns about accommodating a larger crowd. So it's really great to see all the enthusiasm and how people really wanted to come and be together after our 3-year break to share exciting results. We had really good, healthy number of students, almost 100 students coming to the CEDAR meeting, and for a lot of them it was their first meeting and maybe first in-person meeting. So really great participation and wonderful to see all of the students. So thank you all for coming and contributing to CEDAR's success. I should mention that a lot of the students are supported by National Science Foundation and with travel support, and thanks to NSF, they were actually able to come. In addition, another number that also CEDAR community is mostly United States based, but we have strong international participation. We had people coming from 20 countries. And picture shows one of activities during the meeting when we organized on Monday, organized student lunch, meet with senior scientists. I'm not sure if it's if I should point. Okay. Some of the largest things that I should mention is really thanks to everybody, to all the members of Science Steering Committee who worked tirelessly on putting this together. Steering Committee has about between 14 to 16 people in different years, and it was for all the year, from CEDAR-21 to CEDAR-22, we worked offline, and it was a real pleasure to come to meet and actually be able to meet and talk and share in person and discuss all of our questions in person. And I should say that working on CEDAR committee steering committee is really a lot of work. And I really appreciate everybody's effort, everybody's contribution, and just to remind that it's countless hours and it's all volunteer effort. So I really hope that you all see and recognize all the work that people have done over the year. Okay, what exactly? Maybe some of you don't really realize, and I assume that a lot of you do not even know that work on a CEDAR meeting starts, work on the next CEDAR meeting starts pretty much even before current meeting ends. And over the year, there were a lot of activities, and in particular this year, steering committee was involved in a lot of things that were not really typical. We organized several decadal survey workshops and tried to steer community and work with community on explaining decadal survey procedures and to organize people about papers. One of the recent features strongly advocated for and organized by steering committee, in particular, Meg Jones and Julia Urbina, is DI activities. And DI happy hours were held regularly throughout the year. So it's not just CEDAR meeting activity, but throughout the year. Steering committee worked on a new CEDAR website. As you all, if you remember, about a year ago, our website was ridiculously outdated. And lots of thanks to NSF, who supported it financially, and all volunteers who contribute their ideas. But I think it looks much better. The long-term future of CEDAR science is, of course, our concern for all of us. And we really try to keep in touch with NASA. Also, a lot of our scientists are supported by NSF, and CEDAR community is a lot of people, a ground-based community. We really involved in a lot of work with NASA missions, as you saw from presentations during the week. And of course, we are thinking seriously about future of CEDAR science that certainly includes future NASA missions. So we organized mission support and organized community to write support letters. So this was also some of the activities that took quite a bit of time. Organized town hall on the future of ground-based instrumentation, and planning for next meeting. Again, planning for next meeting starts at the current meeting. Some of the people on steering committee deserve enormous thanks. And first of all, I really would like to thank our student volunteers, student representative Megan LeMay and Zishun Chow. If you can please stand up. Zishun, do we have Megan? Is Megan here? Maybe she already left, went home. These young ladies put absolutely enormous amount of work and enormous effort and deserve so many thanks for organizing Student Day. They planned and put it together several months before CEDAR. They contacted all the people, developed the program, and I've heard a lot of comments, a lot of feedback that Student Day was wonderful. So really outstanding work, and I really wanted everybody to see and recognize. So thank you so much, Zishun. And if nothing else you get out of all of this experience, Zishun and other students, so it's a great training how to deal with multiple problems, working, trying to solve multiple issues. Okay, CEDAR steering committee, as I said, is completely on a people serve community on a completely volunteer basis, and this is a 3-year term. And this year we have people who are completed their 3-year term, and I wanted to recognize really outstanding contributions of all of them. Astipad was absolutely instrumental in running a lot of steering committee activities, and especially in organizing decadal survey workshops, multiple hours throughout the year. Julio Urbina was like quiet force behind a lot of activities, bringing wisdom to all our deliberations. Jens Oberheid, was one of the first to respond to many questions and address literally hundreds of emails flying back and forth. And Meg Jones was truly outstanding in a lot of different issues and on steering committee. And, you know, all 4 of them contributed really a lot and made committee run. But I really wanted to recognize absolutely enormous effort that Meg Jones put put into long-term running of diversity, equity, and inclusion effort. And as a small token of our appreciation, Meg, if we can, what we have here, a certificate of recognition for you for your outstanding service and outstanding leadership on diversity, equity, and inclusion task force. I should say it really takes emotional effort, not just time, but a lot of emotional energy to bring up and keep talking about really painful issues in our society and in our community. And I see real change in our community since Meg started and organized task force and started, and we had a safe place to discuss these issues. And I really, really hope that this continues. And again, Meg, thank you so much.
Thank you.
As you see, again, lots of thanks to members of steering committee. I think we can have happy smiles that mission is accomplished. I see Megan just joined us. Can you please stand up, Megan? Yes. Again, Megan is student representative from BU who organized, ran Student-The. Okay, moving forward, as we have new energy and on the steering committee, and please welcome new CEDAR Science Steering Committee members. Katelynn Greer from LASP, University of Colorado LASP. Katie, are you here? Can you stand up, please? Yes. Katie's been a CEDAR person since her maybe undergraduate years. And student rep in her graduate student years. So with a lot of CEDAR experience, and Katie brings a lot of energy and commitment to this community. We're really pleased to see Katie joining steering committee. Titus Nyan from Utah State University. Titus is well known for literally decades of work on instrumentation and science with LIDARs and MLT science. So we really welcome and really need his expertise and his contribution. And our new student representative is Andrew Pepper, Clemson University. So thank you so much for joining us, and you will see countless emails in your folder, so please check regularly. I should say a lot of thanks to a lot of other people for making CEDAR a huge success. And I actually see that this is okay, little different slides, some mixture of new and older slides. Enormous thanks go to Astrid Mond for, and you see her every year, every day, countless times here, for really keeping track of everything and keeping everything organized and everything on schedule and answering emails within minutes. And I think she receives really hundreds of emails about CEDAR. And she manages to answer them, to keep everything organized, everything on track, and keep all of it together. I don't know how she's doing together with all the science that she is doing, but enormous thanks to Astrid. Our wonderful CPS team and Michelle Cambridge actually for finding this location under really difficult circumstances and working on meeting logistics on a tight schedule and really making it possible. lots of thanks to Michelle and the entire CPS team. I don't know if Michelle is here, or maybe ladies in the hallway, but they deserve a lot of thanks and a round of applause. Our great audio, video, internet technical team, gentlemen in the back, thank you so much for thank you so much for your professionalism, for your support. We did not have technical issues at this meeting, or if the issues were minor, they were addressed really, really quickly, and everything went really smooth, and we really appreciate your help. And I should say that this is really different compared to some other meetings that we had. So, gentlemen, you contributed a lot to success of this workshop and success of this meeting. Thank you. And last but not least, lots of thanks go to NSF for funding this, for helping to organize it, to working with steering committee, trying to address all the issues, and being very responsive, and really, again, thank you for making it happen. Thank you, Ellen and Katelynn and everybody at NSF. Before we wrap up, just several final action items for you. Consider, if you have not signed yet, consider expressing your support for GDC mission. Again, this is a long-term future of space physics science. We really need those observations and data to move forward with our science. Letter will be sent out this evening, or at the latest tomorrow morning. So this is, if you want to contribute to this, please do so really quickly. We still have 3 workshops between 10 and noontime on really variety of topics. So you have, this is your last opportunity, this CEDAR meeting, to look at what happens at equatorial, mid-latitude, and high latitude, what happens with data models. Reminder to conveners to write workshop summary and post it online. This is what we expect and encourage of all conveners. And again, large reminder about decadal survey. Decadal survey papers that final deadlines will be announced really soon. So please work on them, and while you are still fresh with your thoughts, impressions after the CEDAR meeting, start working on a draft of that white paper. And see you next year at next CEDAR. Do we have additional comments from anybody? Ellen, you want to say a few words? Or maybe here, because they also.
Yeah, so obviously, I think the only person we haven't thanked enough is Larisa. You know, we have this great leadership. Yeah. Yeah, we are really fortunate to have her going through the pandemic from virtual to in person. I think you can all tell that how successful all these past CEDAR workshops are. And I'm really grateful to see so many students and many advancement in many science front. And SF certainly will be really happy to continue to support CEDAR and many of these activities. So yeah, thank you, Larisa.
Okay, thank you, everybody. I guess we have maybe a couple of minutes if you want to express any final thoughts, comments, and so on. If you have any questions, I should say that some of the most pleasant things that I experienced this week is just walking by at some random time, walking by in the hallway, looking at these round tables and see people sitting and talking and discussing science all week, all the time when room is available. And to have time and place to meet and discuss and collaborate is a really big thing for CEDAR, and I was really pleased to see it. I think that this entire venue worked out really quite well. Yes, Zincheva.
Okay, I just want to say some thank you words and some suggestions. I want to thank Larisa and Astrid. Where is Astrid? Yeah. Oh, yeah. These two ladies were amazing. They worked through this whole pandemic with yourself, get sick, and then recover from that. So I really appreciate it. But I also want to say, to fight a pandemic, you need your own immunity. You send me your talk PowerPoint at 1:30 a.m. Then you continue put your final concluding remark PowerPoint together. Where will your immunity be? So take sufficient sleep, okay? Yeah, we all need a good immunity fight. We need to win this pandemic, and then we will move forward with more exciting sciences. Thank you. Thank you.
Thank you, Zincheva. One moment, I see Michelle in the back. Michelle, please wave. Everybody thanks Michelle for organizing CEDAR. I think this concludes our morning plenary session. Please attend our 3 workshops. And after the workshops at noontime, our official CEDAR activities are concluded. And thanks again to all for coming, sharing your science, for, having multiple discussions, collaborations, and I'm happy to see all of you here. Have safe travel home.
Yeah, the student, please move to the stair, right, to take the group.
Yes, group picture.